Okay, my friends, get ready for this. Everybody that's in physics has heard of the effect that it's called the observer effect. So if you're looking at light, you change its behavior. That's what they say. Listen to this. Light behaves differently when you're not looking at it compared to when you are looking at it. They've been saying this forever. It's just not true. The instruments they're using to detect the energies of the light are taking parts of the light away from it. So it's either adding energy or taking some away. That's all it is. Okay, just to give myself a little credibility here, I did all of this stuff, and I mean I did it as deep as you could do it. And this is way back in 1970, 1968, 70, and then all the way up to the rest of my life. And I came up with the conclusion that the transfer of energy is from light into atomic vapor. The light particles themselves become atomic vapor. That is used for everything. It constructs everything there is. And I had to understand this in chemistry, the whole 9 yards. If you don't understand everything about the particles that make up everything, you don't understand anything about anything. You got to understand all the energies, and then I came up with the conclusion that light and everything there is made of dipoles. That's the dipole flood theory, dipole electron flood theory. And we're going to have new books about it, electron flood theory. This was back from 2019, a paper I did. But I'm going to be making new books about everything, because once I realized they don't care about the reality of what I'm showing, well, you got to start over. Because this video I'm showing you right here, you see this? This video has over 1 million hits. And they're talking about, they still can't explain the light, this observer effect, and they're still talking about that. It's not, I can explain it just like that. Okay, let's just get a description of what the observer effect is. In physics, the observer effect is the disturbance of an observed system, which is this light, by the act of observation, just by looking at it. It says this is often the result of utilizing instruments that by necessity alter the state of what they measure in some manner. Precisely. They use what's called charge-coupled devices, and they pull off some of the charge to see what it is, and that alters it, obviously. They sometimes flood light into it, which has nothing more than these particles that I just been talking about, and that obviously changes it. We didn't do that. We used CMOS. All we did was sit way back here and wait for the light to hit us. So we didn't observe it whatsoever. And yes, you can see individual photons with CMOS. Okay, let me just quickly explain to you what all of these different isotopes are. These are all carbon, but they're all different size particles. Why is that? Because this is really what carbon is made out of. It's not made out of a bunch of these big, huge particles. It's made out of thousands and thousands and thousands and thousands of individual little dipoles. And you could take one or two away, and it becomes that. You take a few more away, it becomes that. You take a few more away, it comes that. Or you add some more. But in the middle, there's going to be stable states. This is in the middle. It's nice and stable. It doesn't want to give any away, and it doesn't want to take any more on. Stable, stable. However, as you lose some, they go away, it will want to bring them back. So it'll only stay stable there for microseconds, which is what's called the half-life. All right, I'm explaining to you some serious chemistry here, and I'm making it very simple. All it means is carbon is much, much more than just carbon. Well, what does that mean in an atom smasher? It means when they smash protons on, a proton is not one big ball like that. And when it hits another big proton or a neutron, it smashes into little bits. No, it's a big ball like this. And when it hits another big ball like this, all the little particles go flying. And that's what they're doing in the atom smasher, because they just don't understand what a proton's made out of. It's made out of 1,823 dipoles. Now, if you're going into physics or chemistry or molecules or biology, anything, This is what you're going to have to understand, and you're going to have to pay attention to what I'm telling you, because what you're hearing in physics and chemistry and biology is all wrong. Biology only works because of nucleophilic substitution, which means all of these particles are required. And they break down just like that using enzymes. Enzymes do literally hundreds of years of chemistry in less than 1 second. An enzyme, all done. And it's because it goes all through these different states. But they're only stable for infinitesimal points of time. Some of them are only stable for nanoseconds. They don't know even it's stable for a nano whatever. They have no idea. Oh, it's just a question mark. But these are only the ones that they have seen and know about. But there's literally tens of thousands of particles between every single one of these particles. They say there's only one between each one. No, there's tens of thousands. And that's the only way that biology can work, chemistry can work, enzymes can work, all of that. So if you don't pay attention to what I'm showing you, you're wasting your time in school. All right, so I'm just going to tell you that's just a fact. I'm not bragging, it's just true. They don't understand any of this stuff. So if this is the perfect time for you to be into chemistry, physics, biology, all that is changing now. 100% changes. 100%. All right, we got to have new books. We got to know that if particles are light, space is filled with light. Space is filled with particles. It's filled with dust. We got to go into the mud fossils and how everything changed and how everything was solidified into mud fossils. We got to go into all the other things that I've shown and proven about history and the myth and all that stuff was not just silly. All right, so this is a whole new learning experience, and I'm dragging everything together in here, but that's just what it is. I have understood the chemistry, the atomic structure, why this changed into what it changed into, which is mud fossils. They still don't understand this anywhere. Nobody does. I'm the only one that does. Yale University agrees. They say exactly what I say about the mud fossils. And I say this happened literally within a day or two. They turned into mud fossils. And it was because of what is history told about in 3,500 years ago. Venus almost hit Earth and created a total catastrophe on Earth. And what it did, it literally boiled off the flesh from the body parts and ended up with these mud fossils. And so we got to start right from scratch again. But before you can do anything, you got to understand what particles are made of. They still don't even know how gravity works. I'm not kidding you. They cannot tell you how gravity happens. Why does something hit the Earth? Why? I can tell you, and I will. I'm going to tell you everything about everything, because and then you can confront me and say, no, Roger, that's not right. And I'm going to say, why? And then we're going to discuss it. But right now, it won't be discussed because there's no discussion to have. Because the ones that have made all these statements were wrong. They realize they're wrong. And now they're trying to cover their tracks. They're coming out with a little nibble here and a little nibble there. It means nothing. What it does is it protects them from what's going to be very, very invasive to their way of life, which is just telling everybody, just look at this, look at this, look at it. No. Let's look at the evidence. And then it's going to be a problem for them right now, because we're spending trillions of dollars. We've never gotten a penny back on it. They're still decades away from having any idea what they're doing. And I'll show you how we can get free energy possibly within weeks. Okay, my friends, this is Roger, and I have my friend here, Rocco, with me. He is going to be...
Hi, all.
All right, there he is. He's in Italy. And we are going to be talking about light and about the observer effect and how to explain these unexplained things. This is an astrum. The attribute of light, science still cannot explain. Well, I can explain it, but they have to look at the evidence that's being presented. Now, they're showing that light can be... Well, I'm going to play this. Rocco, I'm going to move you over to the side here, my friend.
No problem.
All right, here. Both of us are up on the side here. Now, let me sit down. Take it easy. And here goes. Now, the observer effect means that, whoops, these are isotopes. I messed up. Well, the observer effect means that when you are looking at something, it changes the outcome, which is crazy. Just to look at it is not going to change it. What they did was they interfered with the energy by either injecting energy in the form of light or by putting in what they call a charged coupling device, which takes a little sample of the charge and says, "Oh, here's what's going on." But they did change it by the device, not by looking at it. So they don't understand this. I was just blown away. They still claim they don't understand this. Unbelievable.
I agree with you.
Yeah.
They completely misunderstood that.
And look at this. There's 1,100,000 hits on this in the last couple months. And this is what is still going on. They refuse to look at the evidence that I have presented. And I presented this to everywhere. And I did go to the University of Geneva in Switzerland online, and I presented all this evidence to them and how we did it and using CMOS. And at the time, they didn't accept any of it, but by the time I was done with the course, they accepted all of it. And I said we focused and we used CMOS, and we could see the particles of light that you guys have been looking for. And I'll tell you about that in a little while, because I also engaged with Fermilab and all the rest of them. And this goes back 8 years ago. Now, let's go into the actual light particles. Now, you can see that, right, Ro?
Yeah.
Okay. All right, so Rocco is going to be looking at this and watching this, and you're going to be looking at this and watching this, and you have questions, or I'm not clear on anything. I want to make it clear. I want to make it absolutely clear. Now, everybody talks about light being a particle or a wave, and they don't even understand that either. It is a particle and a wave. Now, what are we looking at here? You can see the wave, and that is coming through the air, like with my cursor, zip, coming through.
Yeah.
All the particles in the air are atoms. They're atoms. They're atoms of gases and heat and all that stuff. So they have magnetic fields just like the light, because everything has the same field. They're all the same particle. So this one has to push everything out of the way. So it creates a glow, and they glow back at it. A pushing particle against another particle will always create an energy glow. That's what energy is. Energy is mass. Like E equals mc squared. Well, forget the c squared. Energy is mass. Mass is impact. And the harder this impacts, the more mass it has. Now, that is just straight light. All right, it's just starting to accelerate right now. There's a little bitty tiny particle in here, and a huge magnetic field, just like around a magnet. When you take a magnet, it's a little tiny magnet, but around it, quite a ways around it, there's a field, and you can feel that by putting it up next to metal, or next to iron, and you understand the field.
Yeah.
All right.
It's easy to see in nature. So,
right.
If you cut an apple, the section of apple is tolls.
Well, I know, yeah, but that's confuses things. Forget about the apples. This is light.
Yes,
I know. There's a lot of things that look like a lot of things, but this is what we're working with here is that wave. Now, don't forget. Let's go back to the wave. Here's the wave, and there's a particle in here. And that wave is pushing through all the other particles in space, and they are being concussed and glowing. Now the particle starts to accelerate here, and the actual particle, which is right here, is accelerating out of the wave because we are sending it through a venturi. And a venturi crushes the fields and forces it to accelerate. That's what a venturi does. It's what they call an atomizer. And we're starting with light, so we're below atoms. We're making the light atomize. We're making the light turn into the two particles that it is. And you say, whoa, what two particles? Well, here's the two particles right here. This is what that stream, I just showed you that stream of particles. Here they are right here.
Oh, yes.
You see it? So they start over here as neutrinos. They don't have the full energetic value yet. And then they turn sideways here, and then they turn into photons, and then they explode at the venturi, which is this white blob over here. Now here's what it looks like as it's happening. All right, there's the particle accelerating, coming out,
Yeah.
and here is the black separates from the white. They were attached.
That's easy to see, huh?
Yeah, this is fission. And over here is fusion. They come back together. And here's what they look like. And the same particles that Fermilab and all of them see are these two particles, the black one and the glowing one. You see it?
Yeah, the point particle.
All right. This is from Fermilab, from CERN. They all see the same particles. I'll show you what they see when they smash their stuff. We're not starting with huge particles. We're starting with these particles. This is the particles we have right here.
Yeah, the same.
They're the same particles. So, and we see them as light, not as protons. They're smashing huge piles of debris and creating garbage, literal trash. We're starting with this. And when we smash them into this over here, we end up with this. The black ones separate from the white. And only the white ones can squirt through this little tiny venturi. It's very, very small. And they create what they are talking about is muon neutrinos, electron neutrinos, is the black and the white, when they were attached together. And then they separate into the black stays by itself, just like a little ball, and the electron goes into showers. And the showers are very, very, very energetic. They can be up to trillions of electron volts. And we should be able to harvest that energy and use it. And I can't see why we don't do that, because that is raw electricity. That's what you put into a battery. When you plug your stuff in, charge up your batteries, all you're doing is moving that white stuff into the battery. Now, why can't we put a harvester right here and harvest that white stuff as it comes through?
Yes, just before the slit, very near the slit.
So, I'm sorry, I couldn't hear that. Say it again.
Where is much luminosity? You have much energy. So when you put your harvester near the slit, after the slit, that's
right here.
the right position.
Yeah, right. You have to have it right after the venturi. And here's what happens. The light accelerates, and right after the venturi, you would have to put your harvester right here.
Yeah.
All right, because that's what they're showing, electron showers. Now hold on, let me just show you the physics about electron showers. There's no question in my mind that we use light, and the black separated from the white, and these are electron showers, just like it says here. And this muon is the black ball that goes on its own. So we did this. Now let me show you the physics. Hold on one second. All right, I just called up the physics of electron showers. Now, I did show you these are the electron showers. And here they are right here. And we use CMOS to detect this. So don't tell me we didn't detect this, because you can detect individual photons. See this? CMOS image detects individual light photons. And they've known about this since, I think, 29 2009. And 2014 is when we started doing it. And that's when I tipped off the University of Geneva. I said, and this was like 2015, 2016. I went there and I showed them all these pictures. We had all this stuff done at that point. It was all done. So anyway, I showed them this, and now CERN is using the same thing. They're using CMOS. They didn't believe that we could do that, and that's what was now they don't have the observer effect anymore because they're just sampling the light that's coming out. They're not injecting any light in. They're just receiving what's being sent out. All right, if that makes any sense to you. All right, now.
Yes.
So we know that CMOS can see these individual photons. We're seeing the individual photons here, and these are the red ones. But the green ones are exactly the same. Here's the green, exact same photons. They spin much faster, and they have the same neutrinos building up to the photons. And here's the photon really up close and personal. That's what it looks like. And the black one, the green one is the same. The blue one is the same too, but the blue is too fast to really lock into. You see, the blue is just too fast. It comes.
Yes, it's difficult to.
Yeah, you can't see it the way you can see the other ones. And the blue is the one that really sends out the energy. You need to go with the blue, and the reason is the blue, as I will show you in CERN's collider. You see what's happening here? They're sending big, huge particles head on and just making trash, literal trash. Now, you see the blue ones just going and never coming back, but the red ones and the orange ones and all that are just circling around out here.
Yeah.
The blue ones are so close to the dark matter, because the dark matter goes to the center, and all of the electrons collect around that dark matter, and there's just as many white particles as there is black particles, and they surround and crust, and they are so tight though because they're right on the very edge of it. They go and they never come back because you really got to push them. That was makes blue. Then the next layer out is the green, and that can come and go, and the red is just barely held on there, so it just circles around and just comes back. And I can show this here's the green and the red together. You see that? Coming through the same venturi at the same time. The green is very powerful, real high energy. And it reconcusses way out here. It just pushes the red out of the way, because the red is just not a lot of energy. Now, as we talked before about the speed of light, now, and that was a fabulous discussion, Rocco. It was very good to have that discussion, because that really solidified it in my mind as well. Because everybody says, oh, the speed of light's constant. Speed of light is constant. Well, yes, it is. But the speed of light they're talking about is all light combined. So you are seeing the highest frequency of light they can get to is sunlight, basically. And it comes the same speed. And light, brilliant white light does go to basically the same speed. But when you break it down into the red and the green and the blue, they all travel at different speeds.
Yeah.
But when you add them all together, you end up with white.
That's photo, for example. It shows that.
All right, that makes sense to you?
Yeah.
All right, now let's talk about how we can use this energy. Well, first of all, let's look at what CERN does. Here's what CERN does. This is the problem. We started with this particle right here. You see this one down here? That's what we started with. That's light. They start with a neutron and a proton, and they make all these zoo, they call it a zoo, of particles.
And that's the problem, because they lost a lot of time showing that way to
All they think about is the nucleus. I mean, the protons are big, huge masses of gluons and hadrons and all this nonsense. They are nothing more than dipoles. And in outer space, here's what happens. This is in the Russian space station. They made a black hole. They don't realize they did this, I don't think. But what they did was they injected charged particles into a vacuum chamber, and all the black particles separated into the center, and the glowy ones want to be attracted to it, and they push against it, and they push against each other. So the crust, you see where my cursor's going right now?
Yeah.
The crust is glowing because the white ones hate each other, but they still want to be attached to the black. So that's where you get energetic reaction, right here on the crust. And then out here,
we can say there are a kind of impacted zone.
it's just like our solar system. Basically, it's like our Earth. The Earth is ground. It's a black hole. I'm leaning towards the fact that deep inside the Earth there is literally a hole like this that's black. Now,
I agree with you.
it could very well be because all of the white particles are pulled to Earth. That's why the white particles are electrons, electricity, lightning, static. Those things are all attracted to the black particles, which apparently is what Earth is saturated with them, at least. There's a ton of them here. And the other thing is, where did these white particles come back to? Remember, look at this. Where was it? Look at this. It goes, the white and the black is attached together. It goes through, the white gets separated from the black. Are we in agreement to that? You agree with that, right? The white gets separated from
Oh, yes.
All right, no
Oh,
question.
yes.
Well, where did these black ones come from to reattach to these white ones?
There are, I see in that image, there are a little black bird, in fact.
You
The
see,
little black bird.
well, here's my point. If the black ones didn't get through, and only the white ones got through, but normally every white one is going to be attached to a black one, how did these black ones get here to reattach to these white ones? They didn't jump over the top, I don't think. So how did they get out here to start recombining with the white ones? That's kind of a, they have to be floating around in the air, excess black ones.
Or they attach on other particle.
Well, they come back together. Somehow they come back together. Right here they come back together.
Yeah.
So the black ones separated here. They didn't get through with the white ones. So the black ones are floating around out here somewhere. These black ones must be extra that were on this side, and they're jumping into the white ones. And they're reattaching, and they become what they call a Higgs fields. Watch this. You want to see? This is Higgs fields like you never saw before. Boom. Those white ones are coming in, and when you see every one of these fields is when the white one hits a black one, and then they start spinning off together. And that's what creates the light spinning. That's the raw white stuff coming through.
Yeah.
And that's light spinning through. I mean, this was Rod Warren did this work. He absolutely fabulous work.
I agree with you.
Oh, unbelievable! And for years, and
thanks to Rod Warren. Thanks to Rod Warren.
Absolutely. And not long ago he posted this one, and this is light coming through and not completely separating the black from the white, allowing some of the black through, and it's pushing the white ahead of it. The black never gets bigger. The white gets huge and it gets small. And all of this is explained in the atomic bomb blast, where you see the house burning down, and all it does is burn. It burn, and just smoke comes off it. It doesn't even push it at all until the black hits it and knocks it over. And this.
No, you can see that in any video of an explosion of atomic bomb.
Yeah, oh yeah, it's very, very clear. Very clear. So we know the light consists of those two particles in black and white, I mean in red and green and blue and so forth. Now, the other thing...
I have a question, Roger.
Go ahead.
It's possible the particle, the last image you showed, can you show the last image?
The what?
The last image you showed. The photons, red photon.
The red one's here, right here.
Okay. It's possible the particle at the left of that image are tau.
Is it possible what?
If that particle are tau, two black, one white.
Yeah, that's a neutrino.
Okay.
So that's not quite fully formed. Whenever you look up neutrinos and you look up flavors, they say
Okay.
when you talk about neutrinos, they can't pin them down to an energy. They change flavors. They say it's like going to the store and buying vanilla ice cream. And on the way home, which is, here it is, vanilla ice cream over here. On the way home, it turns into strawberry ice cream here, which is the same particle, but it now changes its energy level, so it becomes a different flavor. Then it turns into a different flavor, and then it turns into a photon. And then we split it. They can't do any of that. All they know is that they can see all these particles coming out of this mess. And they say, well, we can see the blue ones, we can see this, and this is a muon, and this is an electron neutrino, and la 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 la. Well,
I think that complicated their work. They just complicate the work.
They're trying to justify their gigantic expenses of these huge machines. Oh, it's
absolutely, yes,
trillions of dollars. Now, did I show you this yet? No. This is the physics of electron showers. The physics. What's that mean? What do you get out of an electron shower? What's the big deal about an electron shower? Who cares? Well, they're trying to make them by using protons and colliding them with other protons and getting all this nonsense to try to get down to where we are at the very bottom is the energy of the neutrinos. And that energy can be 100 billion electron volts up to trillions of electron volts. That means an increase in energy from low energy to high energy. Did they do that test? Yes, they did. And here it is right here. Hold on. Somewhere around here. Here it is right here. Now, don't forget, we're talking about electron neutrinos, which is the electrons. And we're talking about muon neutrinos, which is the muons. Now, this is the track it takes. You see low energy showers? Down here, they're low energy. They don't have much energy. But as they come through and continue to come through, they turn into high energy showers.
That's evident.
Large shower cones are created because one of them hits another one, hits another one, hits another one, hits more and more and more, and they hate each other, so they create higher and higher energies. Now, what happens with the muons? The muons bounce back out. You see the muons over here? This is the track of the muons.
Yep.
They bounce back out.
Yep.
Now, and they don't even have anywhere near the same capabilities that Rod has to funnel that particle into completely white, 100%, zero blackness comes through.
Yeah.
Right there. Now, if we could harvest this right here before it gets back
Only white.
only white.
Just white.
And this white, literally, exactly that white is what you charge into your batteries. And that white is what runs a motor. And that white is what runs a light. And it's electricity. That's what you need. And you could do this in a little... Well, let me show you what I came up with. Hold on one second. Okay, we're back again. Rocco and I are going to be looking at what Fermilab has to say about these particles that I have been showing or will show you. And here they are right here. Now, that's the black one. There's the point particle, and this one is the fixed particle. And the black one, just like it says right here. All right, if the particles, the black one is... Well, let's just cut to the chase. This is the summary. In summary, the extended particles, the black ones, have a fixed size. They never change. The black ones, just as I showed you, there's the muons. They may have a fuzzy edge around them, which is exactly what I showed. The point-like particles are mathematical abstractions with zero size and literally zero mass that I can determine. They just have an energy field. And here's exactly what he says. It says even zero size particles have an extended effect due to the field surrounding them. It's exactly what I'm showing. And these are exactly the particles I show. And
Yep.
I mean, there is no question. He says they can have a glowy edge around them. They do, exactly. No question whatsoever, that's true. Here they are right there. There's the glowy edge around them, see it?
Yeah, I like that.
And here's his particles. That's right from his... I copied that right out of his article. Now listen to this. Now they talk about space being empty, right? Well, not according to Don at Fermilab. There's the quantum foam. You see this?
Yeah.
Empty space isn't empty. It's a writhing foam of particles. And these are the particles winking in and out of existence like bubbles. And that's because they're light. They're flicking in and out of... Whenever they hit something, they turn on and they show. And here's what it says. The foam on the head of a root beer is a complicated environment, bubbles appearing and disappearing in a dizzying display of change. That is when light comes through dust and so forth. It gets light and dark, and every time it hits one, it's a dizzying little display of particles. It's just like when light comes through a barn, through the crack in a barn, and you can see the dust. They're winking in and out of existence because of the light hitting them. So that's what it's light hitting other things. So empty space experiences that same activity. The subatomic particles wink in and out of existence as they're getting banged. That's the wink. These ephemeral subatomic particles are real and have a measurable impact on our universe. And still they say, oh, space is a vacuum. And light travels the same speed because it never interacts with anything. That's the most nonsense I've ever heard in my life. Here's what space is. You want to see what space is? That's what space is. And it's saturated, absolutely saturated. Saturated with dust.
Where you see electromagnetic field, there are electrons.
There they are right there. Those are all magnetic fields. And that's because every particle has a dipole effect to it. See the black and the white, the black and the white, the black and the white, the black and the white.
Yeah.
This stuff up here, I can't explain. That I cannot explain.
That's really strange. It's really interesting.
Here's the only thing I can take away from this. I'm almost not kidding. This almost looks like something like Atlantis. And this looks
Yeah.
like a pyramid.
Yeah.
And these little things are going back and forth from Atlantis to the pyramid.
Let's be real.
And this here is right on top of the moon. I don't know what the hell that is. It's either in between us and the moon or it's on the moon. And anytime you see glow, that's energy. Now, what else do we see here? You see the blue?
Yeah.
It means this moon is going that direction, and the sunlight that normally would bang on there is being crushed, turning it blue. It's the opposite of the redshift. Redshift they think is light pulling away. Redshift is just light slowing down, and it's becoming more strung out, like the spring being pulled and stretched. And you can't see this, I don't think. Well, maybe you can. You can see that in here. This is what.
Yeah.
That's what red is. This like this wide. This is what green is. This is what blue is. And it's a particle spinning. It's a particle spinning. It's not a wave. It doesn't flap and like that. It spins. And can I prove that? Absolutely. Everything I say I can prove. I'm a material scientist. I am not a guesser. And here is the particle spinning. And again, this was Rod Warren. He's the guy that should get the credit for all of these pictures, basically. I did some of this, but not, and some, I had other couple guys do some stuff, but Rod was the inspiration of everything, and without him, it never would have happened. So, this shows everything in one shot. All right, this is the light wave coming through. And all of these particles are the gases in the air. They have magnetic particles attached to them, and they are being winked in and out of existence as this comes through.
You know what, Roger? When I say that image, immediately I think to Nikola Tesla. Because he said electrons move like water.
They are water.
Or they are water, or something like that. Okay.
Here's the deal. Light is a fluid.
Yeah.
Light is a fluid.
I agree.
And this is exactly what happens with gas in an engine. They had Venturis in the gas engines, and they would put a high-speed restriction on the air coming in, and it would make it go really fast, and then they would slip a little bit of gas into there, and it would turn it into atomize it. It would turn it into just like this, and then it would explode in the engine's piston. That's what a Venturi used to be. They would call them Venturi carburetors.
Maybe I'm wrong, but I call that photonic boom.
Well, this is a subatomic nuclear explosion. Right there, that's a subatomic nuclear explosion. That's exactly what it is. The particles have exploded just like they do in a nuclear bomb. And, we might as well show this, because this is the key right here, is that white stuff is the burning part, and it has no mass, which is exactly what CERN and Fermilab says, and the black particle has all the mass and never changes. The white one can get big and small. Now let's see that in the atomic bomb blast. Hold on a second. Okay, Rocco sent me this, which just locks it down solid. After seeing what Rod did, the vibration that precedes the wave, listen to what you hear when a nuclear bomb goes off. Now I'm going to have this very loud, so it may be too loud, but that's okay. We're going to have to do it. Now listen to this. You're going to see the nuclear bomb go off, and then you're going to hear, and then you're going to hear the rest of it. It's a bomb. Here goes. Did you hear that? That is, which is the preceding vibrational wave, which I will show you in a second. Let's go back again to it just going off. Now watch. You see the wave coming across? You see that wave coming across? That's the dark matter. That's the dark matter. We've already been hit by the white matter.
Yeah.
Now comes the dark matter. And the dark matter has all the mass. If you can't decide, if you don't understand the two different things, you will in 1 second. All right, what we just heard was, which precedes the white intense part. So we heard this, then the intense part came, and then we saw the ripple coming across the sand dunes, and then banged with the black particle. So what would the white particle do if it was nothing but burn? Well, it would burn. So let's see it burn. Hold on. Okay, this is Atom Central again, and this is a house that's originally going to be hit by the white particles, which is always what precedes the first part of things out, because they crust the black. And they take off first, and they're the burners. The black ones are just the solid particles, the fixed particle. Exactly what they say. And there's no question whatsoever that the white has no mass to speak of, virtually none, and you'll see that right now. So here goes. This is the atom central. Here goes. Now, and I'm running this at slow speed, but this will give us the understanding. Now, what I want you to watch is all of the poles. You see the poles back here, the wires, everything. Right now what you're seeing is just the brightest bright intense you can possibly imagine, because everything in the air, every molecule, every oxygen, every nitrogen, everything is being hit by the particles. Just like I showed you that wave coming through, all those little particles had to get out of the way. Well, this is just a gigantic wave coming through, so everything's got it can't get out of the way. So what does it do? It combusts. Watch. Watch. All it does, look, you see, I'm going to stop it again. There's nothing moving. This is freaking crazy. This just drove me nuts. Look at the poles. The poles are just smoking. Look at the wires running across the top. They're just smoking. They're just smoking. Look at the house. It's just smoking up. It hasn't moved. Not a single thing's moved.
The particle of that house it's so excited.
They have to absorb a massless, basically, particle. And at that point, they just combust because there's too many particles inside the ball. So the ball, you could see this.
Yeah.
All right, that ball is every molecule is made of these balls. All right, and they're zones they're zones of stability. Now they're not big balls; they're zones of stability of particles. So all of a sudden, you flush a whole bunch of extra particles in, which is just what we're doing right now. And he says, "I don't want those. Get out of here!" And they just explode and they go crazy, and they bits and pieces go flying everywhere. And this is what you're seeing right here. However, all it is they're just sort of migrating away. There's no mass to them. That's the thing, and they're right. That's exactly what Fermilab said, and they're correct. No mass and all the burn. And the black ones have all the mass and no burn. And they're exactly the opposite. Now here comes the black ones. Now watch. It's going to burn, 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 burn and burn and burn until all of the particles are burnt up. And there's almost nothing left to go. It's gone. Now comes the white. I mean the black. And that just knocks everything over. Now it turns around and comes back. You see it? And the reason it comes back is there's a void where it came from. All right, so I still got Rocco going on here with me. Now, here's the deal. I say that there's nothing but particles, and there's just bigger and bigger and bigger balls of particles. Well, what would that mean if we're talking about carbon? Because carbon is right here, carbon 12. and carbon-13 are stable. Well, what other carbons are there? Well, all these other ones are carbons too. These are all carbons. But not only are those carbons, there's thousands and thousands of other ones that are carbons that they don't even know about. And all it means is a carbon is a big ball of particles, a gigantic ball of particles. And there's literally thousands and thousands and thousands. Now, they claim there's only 6 protons. This is the protons. And there's 6 of them, they say. Then they go to the neutrons.
Yeah.
Because they can't account for them, they just throw them in. And they just get heavier and heavier and heavier. So now the mass gets heavier and heavier and heavier and heavier and heavier because they're adding more and more and more and more electron masses. And calling them...
Sorry, Roger. When they talking about neutrons, what are they talking about?
They're talking about 1,824 of these dipoles. 1823 is a charged particle, which is called a proton. But there's 1,823 of these little dipoles. And that is what creates a stable nucleus, a stable proton. It doesn't want to give any up and it doesn't want to take any on. That's what a neutron is. Now, a proton has a charge. So it wants to attract one more electron to it to become 1824, which is stable. All right. Now, if I took 5 of them away, or 10 of them away, or 100 of them away of these particles, it's still carbon. It's just a smaller version of that carbon, which is down here, and it has a half-life. You see the half-life? That means it will try to find stability. All right, and the way it finds stability is to accept another electron or 2 or 5 or 100 or whatever it's missing. All right, and these are the ones that are below the number, which is stable here. See, the masses are small, and then up here the masses are big. They're bigger, and they want to shed these particles off. And here they give them off, and it keeps decreasing the time that it's stable. They're only stable for a half-life of 750 milliseconds, then 193, and then 92, and then 46, and then 16, and then less than 30 nanoseconds. And as they get more and more particles, they don't want them there. That's all it is. Now, when they collide these head-on protons, they think they're protons. They're not. They're balls of these little particles. And there's 1823 or 1824, somewhere around there. And when they hit head-on, they just splash into debris. And here's what the debris looks like. The debris looks like this. They hit them here. You see this? A proton and a neutron. Bam. What kind of dog you got?
my dog, it's like bells.
Yeah, I
Start to
go.
sing.
He wants something. What does he want? Something you want to feed him or something? You want to take care of him?
I just moved my microphone.
All right. No, that's okay. Don't. All right. Anyway, all right. So here goes.
Okay.
Whatever you want. He wants something. He's hungry, man. You're gonna have to feed him.
He like to sing with bell. He like a church bell.
All right. Well, listen. Here goes. This is a proton and a neutron, and that's what they do. They slam them together. You see the big white spot in the middle? When those explode, you get all of these particles.
That's pure energy.
Yeah, well, what happens is they get this. That right there is what we started with. We didn't start with all this nonsense. They get, the X means like 25 or 50 or 60 of these particles in one big glob. So they have no idea. That could be anything. And they see the other ones are the neutrinos. And then they see the photons, which we see are right here. and then they see the red and the green and the blue particles. You see them? The red and the green and the blue.
Yeah.
They see all the same stuff we see, but we started with light. We didn't start with all of that, so we don't have to mess with all that stuff.
The best of your way is it's very simple. It's less expensive.
Oh yeah, by far. Well, and here's the deal. Here, everything is. I don't know if it'll work or not, but according to their calculations, electron showers, as I believe I showed, supposedly increase to trillions or billions of electron volts, which is exactly what they say. Low energy showers lead to high energy showers for the electrons, and the muons just back right out. Now that's from Lawrence Livermore, I believe. That's their articles about this, not mine. So electron showers. Go ahead.
I think gluons, there are a kind of water, okay? And muon, neutrino, it's have a mass. It's a.
Let me show you the muons and the gluons. All you're looking at is right here. The same thing here. The white one and the black one together is a gluon. The black one is a muon.
Muon.
All right. The white one is the electron neutrino. When you call them in their individual names, you have an electron neutrino, which is the white one. That's the energy. You have a muon neutrino. That's the black one. When you separate them through Cherenkov radiation, you create the sterile muon, the black, is a sterile muon, and you create electron showers. And that's exactly what they say. Now, so that's a gluon. Two gluons together are just like two bar magnets. And that is what creates the field around it. And when it comes through, it has to concuss with everything in front of it, and it creates the wave. So that particle is inside of here, actually. And its field is out here. And everybody else has their own little field. It's not like this, because this is coming real hard forward. It's like a car coming forward, has all the mass to it, and it's pushing the air out of the way. All right, my internet connection is unstable. You hear me all right?
Yeah.
You can hear me all right? All right, it's going to be a little slow. But anyway, I'm taping this, so...
Yeah.
All right, so now we come from there to this.
Now no.
All right, this is what we need. Yeah, this is what we need. We need to have a little device like this that people can carry around with them into disaster areas and fire zones or wherever. And it would be powered by this little laser inside, which would be inside of here. But there'd be tons of them, because these are tiny. These are tiny, tiny, tiny. And every one of them could pump out a ton of electricity. So I don't see why you shouldn't be able to have, this have all AC, DC, 110, 220, 50 cycles, 60 cycle, whatever you want. And just contained right in this box. And there's no way it can hurt you. You're only working with light. It's only light. So you're not throwing off these big chunks of particles. When you're dealing with nuclear waste, the reason is the nucleus is these particles here. When you get X particles, they're just too big. When they hit your body, it damages.
I see the image. Stop it.
These big particles can damage you when they hit you. The little white particles that we're starting with light, they can't hurt you. You don't want to put them right on your skin or anything, but when they collect through that laser, no. You may have an internet problem with me, but I'm still recording this on my end. Anyway, all this comes through, and before we listened to that fluttering effect, before the nuclear blast, that We heard that, and that's what precedes the burning of the house. So it goes, and then the house burns up, and the house didn't move, and then the black hit the house, and then it knocked the house over. So I think we've pretty well proven what we need to prove as far as this physics goes.